Good morning, good afternoon, good evening, everyone, for joining us for today's tinyML talk, which is coming all the way from India. And it is by Swarnava Dey, who's a senior scientist at TCS Research. And we'll be talking on the neural architecture search for tiny devices. So, tinyML talks are possible because of our strategic partners who are committed to take tinyML to the next level. And we have analog devices, AI Zip, Arduino, ARM, Compass Marketing, Edge Impulse, Greenwave Technology, Gravity Incorporation, IBM, Imagimab, Inatera, Microsoft, Nota AI, NXP, OctoML, Pollen Technology, Kixo, Qualcomm, Renaissance, Schneider Electric, SensiML, Sony, Silicon Labs, ST, Synaptics, Syntiate, TDK. So our community has been growing, and already 13.9K members in 47 groups across 39 countries, and you can go ahead and join the meetup for getting the latest updates, and also a vibrant tinyML LinkedIn community, which is already 4K members, and it's got 11.6 followers, and it's growing. So we encourage you to join and get up to date with the latest tinyML developments. And we have our on tinyML YouTube channel where all the talks that happens and even the events that is organized by tinyML Foundation you can is uploaded, including this particular talk as well. So you can go there and check the previous videos to get all the more information, all the videos. And tinyML EMEA Innovation Forum is scheduled to happen in Amsterdam on June 26th to 28th this year. And you can go about on the link provided on the screen to look at the events that are happening during this EMEA workshop. And sponsorships are available at sponsorship@tinyml.org. So let me introduce today's speaker, Swarnava Dey, who is a senior scientist at TCS Research, who's been working on embedded vision systems. He is an MTech from IIT Kharagpur, and he is currently pursuing a PhD in robustness, verifiability, and explainability of embedded deep neural networks and neurosymbolic AI. So he has got 30 plus granted patents, 25 plus research papers, and an author of Towards Data Science blog. You can go there and check his work, and also the Google Scholar link provided to check out his research work. So over to you, Swarnava.
Thank you very much, Abhishek. Good evening, good morning, and to all. So this talk is on neural architecture search, and it is mostly targeted for tiny devices. So in our lab, we are basically told that there are three questions that can be asked to a technology: what, why, and how. So for this talk, I have avoided the why and what part. My rationale is that this neural architecture search is there for since 2016. There are so many papers, so many very good tutorials in YouTube from stalwarts. Everyone has explained what is neural architecture search, and I'm sorry that I assume that you already know what is that and why it is good to have something like AutoML. What it does, it finds out machine learning models and deep neural networks automatically. So maybe due to some project, maybe we would like to deliver it to a customer, some customized model that is accurate and efficient. It takes some amount of, it fits within certain amount of memory size, and like that. Maybe that is my goal. Or maybe I want to, I'm writing a paper and I have given a very novel architecture, and I show that it beats any architecture on the world. So I can quickly create some architectures using AutoML, and I can show my efficacy. So there can be several such reasons why you need AutoML or neural architecture search. But what I explain is the how part. I mean, how we can use neural architecture search confidently, how we can download a code from GitHub and then do our required changes. So this is the focus of this tutorial. I don't have very good results and lots of visualization charts. So those things are not there. Only algorithms are there. So, but let's start. So this AutoML, AutoML neural architecture search is the AutoML for deep neural networks. So its research goal for the mainstream NAS is quite well defined. So we are supposed to generate better architectures than human designed ones. And there are benchmarks to prove that. We can benchmark it on NAS bench dataset, write it, test it on ImageNet, and report the results. So if we can push the state of the art, then that paper will be published, and we will also present a good NAS output. But the same goal doesn't hold true for tinyML. For tinyML, we often know the kind of architecture. Often the datasets are not that 1,000 class. They are instead very small 2-3 classes, and sometimes the network architectures are almost known. What we are more interested is that we want to build accurate plus efficient models. So we are interested about the SRAM usage, about the latency of the model, energy usage. So the goal is different. The search is same, but the goal is very much multi-objective. So in this tutorial, we try to explore what are the possibilities for that. So the mainstream NAS community is not focusing on tinyML. We have to do what we need. So this is what we hear. Whenever we read a new paper or listen to a new tutorial, we hear that the state of the art in NAS is differential one-shot NAS, that is darts and darts based NAS. So it's true that this is a paradigm shift in NAS search. So if you, it only takes a little bit more memory because it searches a supernet, and that's it. If you have a good GPU machine with memory, then you can run darts. So it will work out of the box. It will work and produce a good architecture. But there is only one objective: accuracy. That kind of model will not work in tinyML. So it's a large model. It takes a lot of resources. And if I have some preferred objectives, for example, I have a budget on the SRAM, I have a budget on the size and latency, this will not work directly. We need to tweak this. So that is one myth I wanted to bust. Another thing is that the heuristic and sample-based NAS, which are very easy to work in a multi-objective fashion, where it's very easy to integrate our preferred objectives, those are obsolete. So you don't, though NAS started with reinforcement learning, people don't use it anymore because these darts and other differential NAS, these are actually the state of the art for searching very large architectures, for searching them fast. But at the same time, this is also not true. So we have to use this kind of NAS as well if we want to, at least currently, until something good is invented. So in tinyML, our focus is not large, many-layered networks and with very complex connections. We want accurate multi-objective conformance and platform support API. For example, I need a TensorFlow Lite as my output. And if I use darts, it will be using so many types of operation. And finally, when I try to convert that to TensorFlow Lite Micro, I'll not find support for many of those operations. So this is a setback. So that those kind of things will not work. I'm not telling that it's bad, but I'm telling that it's not suitable for our purpose. There are direct NAS for tinyML, for example, MCUNet, V1, V2, MicroNAS, MicroNet, but they have their own merits and demerits. Sometimes we don't have the preferred objective. Sometimes the code is not amenable to changes. So if you understand NAS well, then we can do all these things. We can play around with the things that are available and use this very useful tool that is AutoML for neural network search for our own use. So this is my agenda today. That is, first I'll do some state-of-the-art study and how it aligns to tinyML. Then I'll teach a naive method to generate deep neural networks. And then I'll be enhancing that method using reinforcement learning. And I'll also cover some sample-based NAS techniques with different optimizations. And finally, I will come to gradient-based NAS. So after I show about gradient-based NAS, I'll tell about some take-home points. And so let's get started quickly. And okay, so NAS actually started with reinforcement learning, and at that time, a recurrent neural network was used to generate architectures. Architectures were treated as strings, and those strings are generated via RNN. Like RNN generates language model strings, similarly they used to generate these neural architectures. So that kind of NAS was very compute heavy. They took huge number of GPUs days and are not useful. But those were the pioneer systems. And around the same time, there was also a Q-learning based NAS, which is called MetaQNN, more known as MetaQNN. This NAS was also reinforcement learning based, that is Q-learning based, deep Q neural network. But this is quite useful because it doesn't have the overhead of RNN, and when the search space is quite small, this works well. The next two big innovations were the cellular search space. That is, when the network becomes very large, we are basically searching for the layers one after another and all the hyperparameters that are within that layers. So it becomes a very large search space, and there is a sure chance of combinatorial explosion. To avoid that explosion, people divided the network into smaller spaces and created the cellular search space. So this NASNet paper was very famous. And after that, the next innovation was parameter sharing, which was brought in by ENAS paper. This ENAS paper showed that we can train a very large supernet and treat all other networks as a subset of that. So that way, the big training has to be done only once. So once these two innovations were done, they were all applied only on the RL-based NAS. But at the same time, people came up with other optimization techniques. So this is very common. If we can solve a optimization using one optimization technique, people try using other optimization technique to solve the same problem. So for that, this evolutionary algorithm and Bayesian NAS, they were started getting used, and these optimizations are more approximate and faster. So they also push the NAS state of the art. Then came the game changer DARTs, which I already told about. It used most of the earlier innovations like cellular search space, parameter sharing, and then it came up with this one-shot gradient-based approach. And it actually, the several times training of large number of architectures, all were removed after DARTs came. But those, as I already said, that those are not this searching of very large, very accurate networks are not really our goal. So the goal that is important in tinyML, I'll tell them in the next slide, but we can for our own, it's worth remembering this MetaQNN paper for the very efficient optimization method based on RL, the NASNet paper for the cellular search space structure, ENAS paper for parameter sharing, DARTs for this first one-shot differential NAS, and aging evolution and Bayesian optimization based NAS as milestones, because these will be required in future when we study more advanced tinyML NAS. So 1000-layer DNNs are not actually our target. We have found in our practical experience that 20-30-layer DNNs works quite good for small tinyML use cases that we solve in our lab. We mostly work on healthcare datasets with 1-2 classes, yes, no, and there these kind of DNNs are produced very quickly, and we can do the global search space-based search also. There sometimes the interconnects are complex. I mean, this network is connected to this layer, is connected to some other layer in a fashion which is I may not even think of how that happened, but the software did that. AutoML finds out unexpected connections, but that is already shown in SwiftNet paper that such things are possible, and it increases accuracy. So my point here is that training smaller model marginalizes many problems that we saw. So that is the advantage that we have over the normal NAS. But for tinyML, these other factors are very important. How do I get the model size? How do I get the peak RAM usage? Do I measure the whole RAM during the evaluation? Because accuracy measurement is quite easy. So when we are training, we just test the model on the test dataset. Done. But the other parts are not easy. How do I measure energy during each cycle? Or I approximate that energy? So this measurement of key performance indicator, engineering the reward, this becomes very important for tinyML. So for example, this MCUNet V1 and V2 from MIT, these shows result which is I would say mind-blowing. So first thing is their search space reduction technique is very interesting. So they say that within a given SRAM budget, they only select the models which has the highest flops. So the rationale behind this is a model with large number of flops will have better accuracy. That is what they have seen. And now they want to budget the SRAM based on their tiny platform, and then find out the models only top K models with top K flops. And they are quite sure that those models will have high accuracy. After that, they do the search. So these are the kind of innovations that we often see in tinyML. But I don't know. I mean, some people might say that I want to avoid large number of flops because it may make a model accurate, but there is a chance that more flops may mean more latency. So I would do the other way around. I'll budget the flops, and within that I'll find the model which has the least SRAM. So for that we have to take this MCUNet V1 framework and then change the code. If we understand the optimization, if we know where we have to change, then this kind of things becomes very easy. Another thing is these MCUNets are very much closely tied with their tiny engine IR format. So they have written this hardware runtime for themselves, and that becomes a pain for us because some of us would like to use TensorFlow Lite Micro, or for example C code for inference. Then it becomes a task to convert this tiny engine IR to other formats and write some automation there. So these are very good, but they have their demerits as well. That's the thing I'm trying to point out. Then MicroNAS, it's also a famous paper. It uses the aging evolution and BO. None of these tinyML NAS papers invent their NAS algorithm. Rather, they use some existing NAS and they try to incorporate these points that I mentioned, how to measure the KPIs, how to do reward engineering, evaluation, etc. So they do something. They add a very interesting constraint that I'll select only layers which have less hyperparameters. So that's what they name as their working set, because these networks are, if it's not a a high-end GPU, these network layers will be executed sequentially. So at any point of time, I'll be loading one layer to the memory. And if my one layer has very high kernel size, so it becomes very difficult to reduce the peak memory usage. So that is how they reduce the PMU. They also consider MAC as a proxy for latency. And adding those to aging evolution and BO framework, they create the microNAS. And microNAS is very promising. It says that it has darts plus latency memory energy. So this is quite good. The only problem here is that they approximate everything by flops. So they have a proxy that flops into something is latency, flops into something is memory, flops into something is energy, and that they put into the darts loss function. And that part is also not clear. Dart loss function plus some regularizer. This is what the paper mentions. I have also checked their code, but I'm not very sure about this part. I'll come to this later. And another thing is there is a paper in CVPR 2020, latency aware differentiable neural architecture search. So this is the only one mainstream paper I have found which tries to do a multi-objective differential NAS. So it says that MAC is not a good proxy for latency. You can read this paper if interested. The second part is reward engineering. So now accuracy is not the only reward. The reward is also different other objectives. So these tinyML objectives are often Pareto optimal. So you know Pareto optimality, that is one object cannot be improved without making other worse. So if you try to make one accuracy better, size or PMU may be bad. So we want to come to a balance, and that balance can be the easiest method is to treat all other objectives as constraints. For example, my RAM is a constraint this size, my size is a constraint, maybe 256 KB, and I may not have more than this number of MAC. If I encounter models, then I have to discard those. So that's the easiest method, but there are other methods as well. For example, in DPPNet, this is not a tinyML paper, but it was a fast paper. It did it in a very crude way. So it connected the actual hardware, and once a model was generated in the same loop, it tested that model on the actual edge device, mobile phone, and then found out the inference time, memory usage, and put that into the optimization objective. That took a lot of time, but that was the starting point. Then we had MONAS, which started doing scalarization. Scalarization is nothing but taking these different objectives and trying to come up with some coefficients which ultimately make them a scalar value. So this is not easy. For this, you have to do some kind of experimentation. You have to find out and learn this alpha, beta, gamma, the coefficients in a hard way by doing experiments, and you will figure out that some combination will work for your particular use case. For example, if you have very high accuracy dependency, you may write this as 0.9 into accuracy plus 0.10 into energy, or the other way around. So this is scalarization. There is a very good scalarization used in microNAS, where this lambda t1, lambda t2, these coefficients are time dependent. So after a certain amount of time, I'll sample new values of these, and that way there will be a mix. That mix will ensure that all the objectives are given random values. So this is where the innovation from the tinyML community will come. It's not about designing a new NAS optimization or a search space. It's more about how to integrate these KPIs into a NAS framework. Now, with some covering of the state of the art, let us move to the actual problem. So this micronets and darts issue I have already raised. I'll come back. So let's now start to learn how neural architecture search works. So we have an input image X, and that input image is height into width into channel. It comes from an input space X, and we have labels Y. So now we are trying to learn through neural architecture search a mapping eta that takes x, y, and my performance parameter and generates me a network n theta. This n is the neural network, theta are the parameters. So this n theta neural network can also be expressed as a composite function, where each layer n1 theta, n2 theta 2, and nm theta m, these are all my individual layers, and individual layers have their own parameters, theta I. Why I am trying to split it up? Because I want to build the network sequentially. That is my target. So ultimately, each of these layers are some functionalities, f1, f2, like that. And these functionalities are actually some affine transform or a nonlinear transform. It's nothing more than that. So this is what this kind of if we can build a composite function like this, then we can convert it into a n theta. That n theta in PyTorch may look like this: conv d, relu, maxpool, etc., etc. So first we need a search space. So let us decide that we assign some identifier to each component of the architecture. So let the architecture encoding be, I have my layer type, for example, conv2d, and then the input to the conv2d and the output. So usually there is an input image and then output feature map, the kernel size, stride, padding. So this becomes the encoding for first layer. So similarly, I can have a encoding for second layer, encoding for third layer. So I'll have a variable length string encoding. That encoding will uniquely express my network. And if we see this conv2d, for example, okay. So if you see the conv2d example, this table gives all the kernel values, the different operations, their kernel sizes, values, etc. And we can put these values as is and use only the categorical, for these categorical operations, we can use a ID, identifier. So that identifier is defined in the last table. So this is how we can create encoding of a network. So this is my search space. Now let us see this naive NAS designing algorithm. Can you all see my presentation?
Yes, we can see.
Okay. Okay. So here we, so I'll line by line I'll express. While some reward is less than my maximum desired reward, for each layer L, I'm trying to build an architecture like this: layer 1, all its parameter; layer 2, all its parameter; layer n, all its parameter. So here is the algorithm. For each layer L in layers, that is the maximum number of layers, for each h in the params. So you know these are the params: param 1, param 2, param 3, and these will have the values like 1, 2, 3, 16, 32, something like that. I randomly assign one parameter from the value set. These are discrete values to that particular layer and that parameter. So I in the for loop, I am trying to build one layer and append that layer to the architecture n. I start with an empty architecture n, and then I am appending each layer. For each layer, there is a param. For each param, I am generating a random value. And then I'm converting that full string to a architecture, that architecture n to my n theta. That n theta is the PyTorch realization. Then I train and evaluate n theta, and I get accuracy, size, RAM, MAC, whatever I need. Then I do a conversion, scalarization of that into a weighted score row. So first, initially the string is empty. I can also take a full network which is already built, and if you see this right hand side box, for each param I can just randomly change that value. This is also called morphism. This is also called morphism or mutation. In many NAS algorithms, you don't start with an empty architecture. You start with some architecture, some values in the params of the layer, and then change that randomly. But remember, everything is done as a random choice. So this is my NAS algorithm. So if I run this, I'll definitely get one architecture N, and I'll get an architecture as output, which will run, and it will also have have some accuracy, some size, and RAM. So unfortunately, it will not be a good architecture. So the problem of yes.
Yeah, so there's a question. So by Alexander. So on slide number 22, is this the random search? Is it similar to applying Monte Carlo technique?
Monte Carlo, yes, we can also do that by Monte Carlo, because we are basically trying to generate lot of random values. So we are doing Monte Carlo simulation in one aspect. But here we can consider this as a very simple random for loop, and we can, I mean, we are trying to generate an architecture randomly, a string. So yes, it's we can also do it using Monte Carlo sampling. Okay, so the problem of naive NAS is it learns nothing. Better architecture are not generated progressively. That's the problem. I may get a good architecture, I may not. If there is a chance, and if I have a very good sampling, like the question said, that this random function is ultimately a random choice, right? So if I can write a random function which always returns good values, maybe a superior version of Monte Carlo, then I can, but then also I cannot guarantee. It's always random. I can get a good architecture, I may not get a good architecture. And the most unfortunate part is I am not learning anything. Moment my agent creates a good network, it may again create a bad network. So how to make this search intelligent? So we have to consider and incorporate the feedback that is generated from the evaluation of the network. That is the accuracy, size, RAM. From this, I need to take some feedback, which we are not taking here. And we should strive for generating better architectures. But however, sometimes it works very well. So if you see this paper, this is a ICML paper, unbelievable, that random search and its reproducibility for neural architecture search. So this is a very interesting paper. It says that random search is not bad. But here I use it to introduce you an algorithm, which I'll be using in the next slides. So only thing that you need to understand is that this same random search we can make better, naive search, but we have to put it into some existing formula. So these formulae are, for example, reinforcement learning or Bayesian optimization or evolutionary learning. So here we are not trying to understand that technique or why it works, rather how to put my algorithm into that form. So it's like a plus b whole square, that formula I know, and I'm trying to put my a and b here. So we model the NAS agent as a Markov decision process, where there are probably 6 state transition and then some actions from different states. So the agent starts with the initial architecture N that we have seen, that empty architecture, and that is its initial state. So these states are associated with this network, and they are identified by a state vector. The state vector is this one, the old thing that we have seen, this layer 1, layer 2, layer n. So first state vector can be layer 1. The second state vector, layer 1, layer 2. Based on that, there will be the third state vector. So it's quite simple. So we only need to understand our own problem clearly to put it into a Markov decision process or a Bayesian optimization. That's my point. So so from one state to another state, that is from one layer architecture to another architecture, we can generate by modifying the n, which is this n. And modifying n is taking some action. So these are terminologies of MDP. So there can be several choice of actions from the current state. Yes, this is what we want exactly. We need the choices. For random case, we had no choice. We just took a random value. But for moving from one state to another, that is one encoding to another, from sequentially adding layers, I should have some choice from the current state. So why are we doing all this? We want the agent to choose the best actions. So the agent aims to take actions such that a reward value is maximized. Reward you already know. I told about reward engineering that is calculated from my multi-objective. And then the reward represents the feedback that the agent receives from the environment. And for example, the reward can be validation accuracy as well. This is true for mainstream NAS. So the agent actually takes two types of reward. One is the immediate reward. Row T1 is the current reward, or row T1 plus some discount factor into the future rewards. Future rewards is kind of look ahead. So if I add layer this con2D and then add max pool and then add a batch normalization, this will be the reward. But I'm not very sure about the future reward, so I add a less than one factor, that is the discount rate for this. More the future, more the effect on that value on the reward becomes less. So now we want to associate one value to the state. So on a certain state, that is the layer is being built, the total network N is built till layer 3. For example, layer 1 I have added, layer 2 I have added, layer 3 I have added, and I am in the state CT1. I want to add one more layer. So I need to understand the value of my current state, and on that value taking an action, that is morphing one part of the architecture, changing one param to other, some discrete decision. So this value is expressed as, so this is what I referred initially. This is a formula. I cannot explain how this works, but it works. So this value of a state is CT1, comma, alpha is the action, is the reward alpha, that reward that is generated when I go from CT1 state to CT2 state, that is I add one more layer or add three more layers, and the reward that is generated plus discount rate into the reward that I get, that is the value of the state CT2. So I start from CT1. This is my current state. I'm trying to calculate the value of this state on an action alpha. Alpha is some change in the network. So I'm taking the immediate reward from going from CT1 to CT2, and also with discount the value of all the rewards that can come from the state CT2, its total value. Now, to approximate this, it's very difficult to calculate this cumulative value. I have to go to all state transition, I have to find out all the paths possible, and it becomes intractable. So people created a policy called epsilon greedy policy. This greedy strategy considers that I can choose the maximum path and its reward and take that as my future reward. So I am greedily choosing the maximum path. So this is my formula. So once I have a formula for a current value of a state and the action, the agent has now power to choose the correct state and the correct action on top of it. This is exactly what we want. So now I'll show.
Yes, Swarnava. So
Yes.
with respect to the future reward, so there's a question that asks what point future reward can be estimated? Is it already known when selecting a good next state?
It's not known. I mean, the future part is something that we don't know, but initially everything is random, but slowly we tend to understand what will be the future reward from our experience. But the point to note here is the future reward, we always greedily choose the max of the next state. That is, we are not bothered about the whole state transition, but we just want to take the next maximum reward that is coming from it. So, so it's very, I mean, it's not very easy to do, because here, if you see, train and evaluate m theta to get accuracy, size, RAM, and MAC. So we have to do this for all the choices. So if I have 10 actions from a certain state, I have to 10 times I have to calculate this. And then I have to take the max. But still, with a greedy policy, I'm avoiding going through a certain path and all its possible states. But I'm just grabbing the maximum one. So this is the same naive NAS algorithm. So now we start with the architecture N. We have an action set A. This action set is creating of a new change in the architecture, and then a set of states C that is partially filled by layer 1, layer 2, layer 3. And now while this row is less than max score, the same thing that we did there, here we are trying to do the same thing. We are taking for L in layers, for H in params of that layer, we are doing a random choice of values H and append L to the architecture N. But only thing is, this time we update the set of actions with alpha, the action that we actually took, and this random choice is a kind of action. I changed something, I added a random choice. So that random choice I encode into an action alpha and I update that with A. And the state C with Cn, that is till what point I created the network. Then when we do this and create a architecture, see, only difference is here I'm updating and keeping a record of my actions and my sets. And then I convert the string into the neural network, train and evaluate it, convert accuracy RAM back into weighted stored P. So I name this part as explore, I name this part as evaluate. And then for all my states in C, this C is the state set. And for all the actions that I have taken, which is encoded in this alpha set, A set, I use this Cn, alpha, reward, and the values of each state to train a new network in theta. Here is the chain. So I'm basically creating a data set out of my actions, and upon taking some action, what is the reward I am getting? So initially I know nothing. I'm just doing this exploration. It is the same as naive NAS. But slowly, as time progresses, I'm using this as a machine learning data set. And I'm training another neural network which has a mapping of the current state and all these parameters that I have used, and it will give me the best action. I put the current state, it gives me the best action. So the final algorithm for RLNAS is very simple. While my reward is maximized, if the random value I'm generating, I'm testing it whether it is less than epsilon, which is my policy, I'll do exploration. Exploration is what? This thing, this randomly creating say architecture and appending that to my data set. Once I do, and then if this random value is less than epsilon, then I'll not do exploration. For L in layers, I'll directly put my current state, that is I am till layer 3. What should be my layer 4? What change should I do? The neural network will tell me what change to do. And then I'll add that layer to my neural network. And then finally, I'll evaluate. Evaluate, you remember, I create the architecture, convert the architecture into a neural network, and then do all those KPI measurement. So this is a policy. This policy is called epsilon. So this policy, initially I do a lot of exploration. If I don't do exploration, I don't create that data set, and I cannot train my neural network for that. And once I have done sufficient amount of exploration, I'll be able to exploit this neural network to take decisions. At that time, I don't need to randomly generate value. I'll always be doing the good network generation. So that's the RLNAS. So I'll give a case study on RLNAS that we have published in Perform recently. So you see, if in the left-hand side, we have the exploration rate of 1. That is, whatever value I generate will be less than 1. 0 to 1, I'll generate a random value. So what I mean is, initially exploration rate is very high. So I'm doing a random choice, and so on. And finally, I generate a reward and store the pair of all the actions that I have taken on and how sequentially I have built the network. Then exploration rate is reduced to 0.9, and I take all the random decision. One action is actually coming from the deep neural network. And then again, I calculate reward in this way. As the search iteration increases, I reduce my exploration rate. And one day, I'm telling in days because this takes days to search, 2-3 days. So this exploration rate becomes less, and whenever I try to search a network, I immediately search this. So because when my exploration rate is very less, my exploitation rate is high, then all the actions are coming from deep neural network because it is now trained. It knows that given this state, given this combination of layer, I must take this action to get the next best layer, and that will give me highest accuracy, size, etc. So this is how this NAS operates, and we implemented that based on MetaQNN, and we solved the ECG atrial fibrillation, one flagship use case that we do in our lab, smoking episode detection, hand gesture detection on the ego gesture data set. And usually, for example, this ECG AF, we did 3000 iterations in 90 hours in a A100 GPU, created 20 layer 225 KB model with a very good F1 score, which is comparable to the expert design model. And here, the multi-objective reward that we used is accuracy, size, SRAM, and MAC. And this is how we designed our reward. That is, one is we took accuracy with the highest weight and summation of all other weights into e to the power other objectives. And we divided everything by the summation of all the weights. So this is something that we invented. I mean, after a lot of experimentations, we found that we have to meet the F1 score, and we need to prioritize the accuracy under any circumstances. But the other objectives, we took a exponential version of those objectives, weighted exponential version. So that ensured, and after a lot of experiments, we found that if you see the left-hand side graph, that when the topmost graph reward goes to maximum, the accuracy is maximum, model size is also less, the number of max is also coming to a good level. And we found some very good Pareto optimal objectives for the model sizes also. Different fronts of clear good models are available. So this is where the innovation will come. Based on our data set, based on the particular data set that you have, you may have to design a different reward, and this designing a reward for a particular problem is a age-old problem. With good intuition, we can do that, and we can put it into any existing NAS. Another very important thing is when we train this M theta network, there is a new research field that how this M theta transfers to a different problem. This is called offline RN. It's a hot topic nowadays. So once I train it on one problem, how do I can I use the same M theta for solving another problem? So I don't have to explore and do all these things right from the beginning. I can just take this network, do some transfer learning on that, and use this network to neural architecture search on a new kind of data set. So these two, this one is a very new problem, another is an age-old problem, this good reward engineering. Based on that, we created this system.
Yeah,
I'll
so
also
now,
tell, yes?
so there are like a couple of questions on the RLNAS. So what from the looks of it, the exploration rate looks like a hyperparameter, right? So
yeah,
yeah,
it comes from greedy epsilon greedy policy. So I start with a high exploration rate, and slowly I decrease that to a very low exploration rate.
right. And so what other specific hyperparameters are used here?
This exploration rate is the hyperparameter.
So that's the only hyperparameter we use, is it?
Yes, that's
And
important.
so what is the optimal rate in the experiments for this explanation rate where it actually is the causes the best outcome?
I don't remember. I mean, it starts from 1 and then slowly decays to the zero value. So it's case to case. We have to try and experiment with that. I mean, this is a very fairly standard process. So there is a decay schedule, and using that decay schedule, we usually reduce the exploration rate. And if it fails, we just change the decay. Like in training, we change the weight decay. So if you ask me, like in Adam Optimizer, there is a SGT, there is a 0.009 weight decay or something. That kind of thing is not here. We have to try an experiment. Any other questions?
You can go ahead. Yeah.
Okay. So now I'll just touch upon this evolutionary NAS. So the evolutionary is not NAS is the AE NAS is not at all like this, but I have brought everything in my tinyML algorithm. So I'll try to tell about EvoNAS. So in EvoNAS, we create a population, and then from 1 to max score, we generate a neural network N and my action space. You remember the action space that came out in this algorithm? So we take action and we change the state and then just create this A. It gives all my architectures. This is my exploration. The same exploration remains here. And then I evaluate and get the reward row. And I start with an empty population. I append this to this neural network architecture. All the actions that I have taken, all the rewards I have obtained. Then I set something as mutation rate 1.0. That is, high mutation will happen. And this is again like that exploration rate kind of concept. So there is no known formula, at least I know, but we usually start it with 1.0 and usually reduce it with a certain decay formula. So I tell upfront here. So from 1 to the maximum score that I'm trying to get, I choose a parent from the population, which is the fittest one. Fittest one means the highest accuracy, size, etc., etc. And then I mutate that parent to get a child. So what is mutation? This is the critical function. So like in RLNAS, we had a critical function where we trained the neural network to take decision. Here, this mutation is a bio-inspired function. I can use some kind of aging evaluation. I can also do some crossover, etc. And as it's bio-inspired heuristic, it's supposed to work. It often works. Then I create a child, and from 1 to max score, once I do that, see here we are just increasing the population. I have a population, I'm doing a lot of exploration and adding to this population, and then I am slowly taking a parent from the population and mutating it to create a child. And then when I create that child, then I evaluate that child and again append that to the population, and finally remove the least fit one. That is, slowly I remove all the weak models which has less reward, and that way I keep a very good population and I do selective breeding, and then I update the mutation rate. This is again some formula to change to reduce the mutation rate. At last I'll have actually no mutation. So the final architectures will be the top K based architecture in the population. So in the same framework, so my point here is actual implementation of AE NAS is different a bit, but once you know one NAS well, maybe the RL NAS or the any other framework, even the random NAS, random search, every other sample based NAS is almost similar. We just have to use this as a formula. We have to encode our architecture search as a string problem into that formula, and we are supposed to get good results out of it. So points to note here is that the main approach is sampling architectures randomly, evaluating and learning to sample better architecture in an informed manner. And we are building the network sequentially, one layer after another. And then the reward here is completely decoupled from the search. So if you have noticed that in the RL NAS also, we have a completely different evaluate cycle, and in that evaluate cycle, we can just generate a multi-objective reward using all those accuracy, size, MAC, latency, whatever we can arrange from the platform. We can take and create a scalar value or create a optimal front, have other as constraints, and then use that in the search process. So under no circumstances this reward is affecting my search procedure. So it's completely decoupled, and this is the biggest advantage. And all these layers have discrete choices. So these are the main points of sample-based NAS. And now we come to differential NAS, which is called DARTs. So DARTs, the main innovation, it uses a fixed network of a number of cells. That is, it pre-decides that there will be this many number of cells in the network, and then it predefines the architecture where each cell has two inputs and then a concatenation, and in that way. But this is not their biggest innovation, because this was already innovated by NASnet, if you remember from my initial slides, the cell-based structure. And these cells will have internal connectivity. So each cell has nodes, node 1, node 2, node 3, node 4, node 5, like that. And they can be connected in many different ways. So there can be a connection from here to here, here to here, here to here. So I'm only supposed to search within the cell. Within the cell, there can be different connectivity between all the nodes, and I have a predefined manner in which all these cells are connected. Now, this is also not their biggest innovation, because this is also part of the NASnet and ENAS. So they have used this innovation, and they have used this concept of fixed number of cells. Their innovation is this. So when they start training, look at this diagram A. It says that they consider that within a cell, each node is connected to the other node by all operations. So I was so far showing you an algorithm where I connect one layer, and that layer is a const2D. After that, I connect a max pool. So in this manner, I'm trying to create a network where each node is connected to another node by using one operation. They are telling that no, each node is connected to the other node using all the operations. And this OIJ is the operation that is there from node I to node J, and XJ, that is the output here, is the concatenation of all operations on Xi. So this is X1, this is X2. I concat these two and create a new node, Xj1. This Xj1 is connected to Xi1 and Xi2 by all operations. I'm not sure if it is making sense. So I'm just trying to say that this node in a neural network is connected to another node in a neural network. That is, one tensor is connected to another tensor by const2D. It is also connected by max pool. It is also connected by batch norm. It is also connected by depth-wise separable convolution. It is also connected by some other layer. It is connected by everything. Considering such a cell, they start the training process and see how they are visualizing this. They are modeling this connection as this minus OIJ of X, which means this is a mixed operation. So this mixed operation is a summation of all the operation that belongs to the O, that is the full operation set, and then it is that operation e to the power alpha ij of O. O is a particular operation, const2D for example, divided by summation of O dash, which is all other operation in the set, that is depth separable convolution, batch normalization, max pool, soft termination layer, etc., etc. And so e to the power 1 operation divided by summation of e to the power all other operations. So does this formula look known to you? I think yes, because this is the formula of softmax. So what they're trying to do is, we usually apply softmax at the end of a classifier to find out the most probable class. So here they are trying to do a softmax on the operations. So these alpha are basically the learnable coefficients, which are my logit values at the end. So when I start, I start with all connections having the same state. Then I train the network. Some of the collections become more strong. That is, their softmax value is more. So for example, this is O alpha ij O for operation O divided by alpha ij of all the other. So these things are becoming less having less contribution. So finally, I will have a situation where there will be only one connection that will dominate, and that is my discrete network. So basically, they changed the discrete operation search problem in neural architecture search to a continuous operation search. So they are not saying that two tensors are connected by conv2D. They are saying that 99% conv2D and 0.1% max pool, 0.1% batch norm, which is actually like 19, it's a conv2D. So this is a very good innovation which changed the searching process altogether. So the discrete search, which is not differentiable, now becomes differentiable search. So this is the DARTS algorithm. So first we create a mixed operation for all the edges in a node. One edge is the operation and two nodes are two tensors, how they are modified. So these are parameterized by the alpha ij, which is a coefficient which tells me what is the weight. So this is the logits. So while not converge, update the architecture alpha by descending this, or don't get scared by this formula. So this just tells that I train on the train data set and find the base weight. This base weight is for when I train my architecture on that for a given alpha. This alpha is something that I start with. You remember this alpha? This alpha is the architecture, and that architecture is an architecture with mixed operation. That means it has all the nodes, and when I train it, I ensure that I update it using this softmax kind of formulation. So I do that, and I subtract that from the weight. That is, I do a gradient descent on that, and on the test data set, that is the LVAL, I minimize the alpha, that is the architecture. So in the same bi-level optimization, which is based on game theory, I do a training and find the base weights, and using the base weights, I find the base architecture in the same loop. But again, this is very costly. When I train the base weights on a given architecture alpha, which I start with, then again, this is the pseudo evaluation. You remember, we have to evaluate in case of sample-based NAS. We have to train and find out all the accuracy, etc., size, memory. But here there is no question of size or memory, only accuracy finding. This is a huge effort. So what they have done in the paper, they have proven that for instead of doing this whole training, they can do only one pass of training. That is one epoch training, and that will give them some approximate idea about the base weights in case of darts. So using that weights, now let us find the base architecture testing on the validation set. So what I'm trying to say here is that they created an approximation. That approximation said that they will run only one epoch training on the train set and identify a good set of candidate weights. Using those candidate weights, they will test on the testing data set and fix on an architecture. How to fix on architecture? By training the network in this manner such that one of the operations becomes has the highest coefficient. Now, once they train that, the updating of weights is done on the training set. Using that approximation, we have to discrete the final architecture, discretize, because otherwise this is again this will always remain a mixed architecture. There is 99% const 2D and other operations with some weight. So we have to select the top k from here. Maybe top one will give me one architecture, top two will give me another architecture, another two architecture, something like that. So once we discretize, we do something very bad. We remove the weights of all other operations, but the network was not trained in that manner. It was trained in a different manner, right? So we had some contribution from one operation, some contribution from other operation. So we have to retrain the discretized network on the training data set again. So this is a very involved work, and this is a state of the art, but I have serious doubt about the multi-objective part version of this, because they have proven that for accuracy this approximation works. That is, one epoch training will give me a set of good weights. But what will happen when I am concerned about other objectives? For example, my RAM usage, for my number of the energy usage. So will that be approximated? Can I just train one epoch and do some idea on these other KPIs? No one knows that. And another thing is, when we discretize for the final architecture, slight change and retraining might work for the accuracy, but will it work for all my KPIs? So these things becomes very important. And I already said that I only found one CPPR paper which tries to address a multi-objective differentiable architecture search, which is a CPPR paper, and it has code. There are other papers which are I'll say not trustworthy, because I did not find any code, anything. So that paper is also not contributing to this. So this is an open problem, and unless this is solved, darts cannot be used for tinyML kind of use cases. So my point is like this, that yes, the Moore's law is supposed to reach saturation level. That is, the devices will not have ever increasing RAM, battery, etc. But yes, within 1 decade at least, this increment will continue. I mean, for the next decade. So there is no doubt that we have to search larger network. Maybe 20-layer network, 30-layer network will not work in future. The thing that we are enjoying now, maybe some more demanding use cases will start coming into tinyML devices, and we will be solving very interesting problems of robotics, drone, etc., which may need segmentation and many other things on a drone, or I mean a low power device. So there is no there is no alternative of a multi-objective one-shot differential NAS, and that should be the research direction. We have to do that somehow and solve that problem. But what I tried to show in this tutorial is that for the next few years, we can easily use these sample-based NAS methods, and they are quite usable. They can, all the main NAS methods like MCUNet, MicroNAS, they have used the existing sample-based NAS and integrated their own KPIs. So similar things we can continue doing for at least next 5 years. And if you know one NAS well, you can easily integrate the preferred objectives in the reward function and achieve that. So that's it from my side.
Yeah. Thank you, Swarnava, for that interactive session. And there are like a couple of questions that I think, and if there are more, we can post on the forum. So yeah. So can you, the one question is with respect to, can you please describe what operations are possible with darts? I mean, what are the possible operations?
Dart search space is, as far as I know, it's a very huge search space. So it has at least 3-4 types of convolution, and almost all operations I have seen. But I didn't see anything related to transformers or yes, but I have seen RNN, LSTM, and convolution operation. But the main problem that I would like to highlight is we are often limited by the microcontroller runtime space. So there, in the tiny devices, we don't get maximum implementations available. For example, if we take the tiny TFLM runtime, there is a op resolver.cc file, and that lists all the supported functions. So even if a particular NAS supports a lot of functions, we have to restrict those for our target hardware. So that's the experience that I have.
Okay, and one more question, that one last question we'll take is, can we use few shot learning in any of these architectures?
So this darts is, I guess, it's a one-shot learning. It's a one-shot NAS because it's a one-shot learning. I just train with all samples, but I train with only one iteration. So that is the first order approximation that they have done. So, but I'm not very sure.
Okay. Okay. Thank you, Swarnava. Again, strategic partners, we thank them for their continued support. Executive strategic partners, Edge Impulse, the leading development platform for Edge ML. Qualcomm AI Research, advancing AI research to make efficient AI ubiquitous. Sentient, accelerate your edge compute. Platinum strategic partners are Renaissance. Renaissance is enabling the next generation of AI-powered solution that will revolutionize every industry sector. At Trios, deploy Vision AI at the edge at scale. And the gold strategic partners are Analog Devices, where what if becomes what is. Arduino, easily deploy your tinyML solutions with Arduino Pro. ARM AI, powering tinyML innovation. Inatera, neuromorphic intelligence for sensor edge. Microsoft, SensiML, provides analytics tools suite. ST Microelectronics, which provides extensive solutions to make tiny machine learning easy. Synaptics, engineering exceptional experiences. Silver strategic partners are on the screen. So thank you all for joining us today for this lovely talk, and thank you, Swarnava, for taking our time and providing us the insight about NAS for tiny devices. Thank you, everyone. Have a great day and good night.
Thank you.